In this chapter, your book talks about complexity and chaos. So, physics is usually ruled by some very simple relationships, like the theory of gravity, where we know the mass of object 1, we know the mass of object 2. If we know how far away those objects are, we can calculate the gravitational force between those objects in the Newtonian method. Or, if an object gets very massive, we can use general relativity to talk about how those objects interact. But both of those relationships are well known. What happens though when you put a lot of objects together? Like, for example, all the planets in our solar system. Now, all the planets in our solar system are dominated by the gravitational attraction to the sun. So the sun is the primary source of gravity for all the planets in our solar system. However, each of the planets tugs on other planets, and how much they tug depends on where they are in their orbits. So that changes over time. So even though Newton's law of gravity is a very simple relationship, when you actually try to calculate out in advance what will happen to our solar system over long periods of time, there's actually a lot of complexity in that system. For example, Pluto, being a very small dwarf planet, is greatly affected by the gravitational tugs of its neighbors like Jupiter or Neptune. And over time, Pluto's orbit can change substantially. Earth's axial tilt can change as Earth's axial tilt wobbles because of gravitational interactions between the moon and the sun on the Earth. So even though systems can be subject to simple laws of physics, there are systems that can be inherently complex. So the hope is that studying these complex systems will lead to some underlying truth or knowledge that can't be studied when you look at a very simple system. Like, for example, the formation of our solar system, all the gravitational interactions of all the little pieces of rock and debris. It's really a significant amount of calculation power to try to simulate something like that. And what we end up seeing is when you do simulate planetary formations, even though the initial system is quite chaotic, in the end, most planetary systems you'll get are well-spaced planets in fairly circular orbits, orbiting in the same direction around a star. That tends to be the outcome, regardless of how complex the system initially tended to be. However, many complex systems experience what's called chaos. A chaos theory is that with very similar initial conditions, experiments or situations can have dramatically different results. So even though your experiment might have very similar starting points, you would have very different career paths, different paths and outcomes in your experiment. So a great example of that is weather. We're all experienced with weather, and we've probably all checked the weather. We've gone to a weather app or internet or watched the weather meteorologist talk about the weather on the news. You can predict, if you know what the conditions of weather are right now, what's the barometric pressure of this area and the surrounding areas, what's the temperature, what is precipitation recently, cloud cover, that sort of thing. All those things put together, plus for the surrounding areas, allows you to predict what the weather will be in the future. Now, being here in Wisconsin, in northern Wisconsin, if Minneapolis gets a snowstorm in the winter, chances are, since weather moves from west to east across the state, we're likely to also get some kind of a precipitous event, some snow or rain. But the accuracy of that prediction depends upon how far out you go. So we can very accurately predict, or fairly accurately predict, what the weather will be like tomorrow given the weather today. But looking at the long-term forecast, the 7-day forecast, the 10-day forecast, they usually don't go beyond 10 days because the predictive accuracy drops precipitously at that point. Small change in barometric pressure here or a small change in temperature would dramatically affect how weather operates. There's a famous butterfly effect quote where a butterfly flaps its wings in Hong Kong, and in London you get sunshine instead of rain. So small inputs into a system can have dramatically different results coming out. So that's the idea behind chaos.